Mendoza and Carlo Drada, and today we're going to talk to you about the Humanoid Rehabilitation Project. Now, there is a big issue that we're facing today in medicine, and that is the treatment of children with cognitive disabilities. Now, we know that children do not respond to therapy the same way that adults do, or they're not treated the same way that adults do. And this is more evident when a child suffers from a cognitive disability, such as autism, which is on the rise. Now, if we have a medicine issue, we're, as mechanical engineers, we're trying to figure out a mechanical approach to solve this issue. So we turn into robotics. If we can create a humanoid that works as a inexpensive platform, making therapy more accessible to children, we can fix this, find a solution for this problem. Now, there are many clear advantages to having a humanoid for therapy. First of all, we can, since children are visual learners, we can make the humanoid model the child, meaning if the child has lower strength in one arm, so does the humanoid will have lower strength. If the child has a longer arm, the humanoid can also be customized to have the longer arm or the shorter arm. Another advantage of this is that children with short attention span will benefit from this, because a humanoid is very interesting for children. It's almost as if they were playing. With this robot, we're looking to break this barrier between the child and the therapist, making it serve as an intermediary for the therapist.
So I'd like to introduce a couple of the humanoid projects which already exist on the market. Poppy Project is one we've actually seen already a couple times, and it is a humanoid robot whose primary concern is creating correct anatomic motion. So it's an open source project as well, and it's something that we're drawing a lot of influence from. Autobot is another open source project that is more focused on social benefits for children, and Cherry Project is kind of a merger of the two. It helps with socially isolated children in hospitals. It just gives them someone to kind of interact with when an adult or other human is not present. And I'd like to introduce you to our answer to the humanoid problem. This is Hector, and Hector stands for Humanoid Companion Technology for Rehabilitation. Hector is in his first iteration of design, so this is our prototype phase. Basically what we did with this entire model, which we created, is learn about what are the degrees of freedom which we need in our humanoid robot. So we're concerned with creating something that is similar to a child, so we try to mimic these same abilities as far as range of motion is concerned. These are some of the design components which we're going to be using in our first prototype phase. We relied on the Arduino and these basic servos. In our final design, we're going to upgrade these servos and change to the Raspberry Pi as opposed to the Arduino, and also include a battery for independence from a power source, or a walled power source. Here we have a preliminary estimate of components that we're going to use in our design. So here we don't take into account the cost of filament, the cost of actually printing the design. We have just some basic components. And then in addition, we have here an example of some of the emotions that we've already been able to create with these this LCD displays, which we'll be using as the eyes. So we are doing kind of the parallel track of coding and manufacturing at the same time. Here is a layout of our schematic, or the circuit diagram for the servo. And it just kind of lays out a rough example of our linkage that we'll be using for the arm.
During the prototype stage, some of the considerations that we took care of, for example, one was the kinematic consideration. We were trying to make Hector capable of moving just as a child. For this, we imitate the motion of all the joints. For example, here we have an elbow. An elbow average range of motion is 150 degrees, and what we did was program the corresponding servo to have the same range of motion. Some of the stress analyses for our structure, for our components, were performed for the prototype stage. These studies will be performed again for the final stage, but more in depth. This is just to make sure that our safety factor will be good enough for safety and a proper child-robot interaction. Here we've been simulating, for example, on the left side, 6 times the weight, the overall weight of Hector on the lower part of the leg. Another possible characteristic for Hector, one of our goals on his kinematic capabilities will be to make Hector able to perform some rehabilitation exercise, at least the basic ones. For example, Hector will be able to bend down and pick up objects, walk with or without help, crawl, and all these functions will be remotely controlled via Bluetooth from any Android device.
To build Hector, we're going to follow a couple standards. Our first standard is the IEEE standard, which is pretty much using same vocabulary, same terminology, and same methodology that you see anybody who's deal with robotic systems. Our second standard is our US systems, which is pretty much physical equations that we're going to follow, units, everything, so it's clear and concise for anybody who wants to read our procedures to be correct. Our IPC A610 is similar to the schematics that we saw. It's pretty much a book that's going to help us dealing with wiring, anything, so we know that it's very concise, and if there's a defect, we can notice there's a book, it gives us examples like that. Our last and most important one is our ISO Robotics and Devices Center. We're a Type C type robot dealing with rehabilitation between a human and a robot. So the whole point is, it gives us pretty much standards to, if we're going to use a battery, if we don't want to make sure the robot doesn't turn on by itself. Let's say we have a kid, we don't want his finger to be squished in his elbow. Simple standards that we need to follow by using pretty much adjustments or servo motor feedback, similar stuff like that. For global learning, we want to make it as cost effective as possible. Similar humanoid robots that are out there are a range between $10,000 to $7,000 that do similar functions, but not as the ones that we're doing. Or right now, we're trying to keep it under $1,000. We're ranging around $600 to $700. That just depends on which servo motors we're going to use, because we're not going to use the same servo motors as we use for our elbow here, for a shoulder or a hip, as we would use for an elbow. It's just different considerations like that can adjust our prices, and we can cut down. For accessible to our families, we want to make it easier for the robot to be able to take home. So let's say you don't have to go to the therapist and do the therapy there with the children. With the robot, you can take it home and you can have the therapy with the child, and the therapist can Skype, or he can do anything via chat with you. Our last and most important thing is our open source. Because it was open source for us, we want to make it open source for anybody who's accessible to have a humanoid for their benefit. For possible functionalities in the future that we've taken into consideration, possibility, but we're not sure yet. It would be our sensors providing feedback for balance, something simple as adding a gyroscope into the hip of Hector, keep it a better balance. Another example would be a force feedback joint. There's a lot of technology out there that are trying to simulate joint movement, but it's a simple Newton's third law, action and reaction. We apply a force, the robot applies the same amount of force right back at you. Our broader selection of motor skills, right now we're working with gross motor skills. We can have a possibility to having Hector run, sit down, stand up. It's something similar like that we're looking into it. Last but not least, our source for downloadable library, as we keep saying, open source is very important for us. We're going to try to make a website so we can have accessible for anybody who's out there who can benefit from it. Thank you very much.
How are you going to make Hector childproof?
To make a better answer. Pretty much our standard, it deals with a lot of interaction with humans. There's a lot of stuff we have to take into account. As you can see, he has a lot of gaps. That's because it's our learning phase. Our learning phase, we're pretty much dealing with the connections of servos, dealing with Python, dealing with connections. We're going to try to make them so it's not open, so kids can't get fingers in between it, because it's a high probability,
So is Hector going to be designed so a kid can throw it across the room?
We want to, but that's why we have the stress test, because we also think about that. But like I said,
I don't think in this first and second iteration, right, we have a prototype phase, and then we'll have our final design phase. In either of those, I don't think our intent is to create a robot that is going to be able to withstand the abuse that a child, especially a child who might have cognitive disabilities, might put on it. You know, you can imagine a child throwing this thing across a room. We're not going to account for those things. I think the idea is that this item will always be used under supervision. There's not going to be, it's not a toy, right? It's something that maybe can be used to appeal to a child and serve that intermediary function, but doesn't necessarily indestructible. I don't know if that answers your question.
Yeah, because the problem I have with it is that its function is to teach the child repetitive function.
Right.
And if the kid can't have it without someone remediating that, why isn't the individual that's remediating that doing the repetitive function?
Right.
So where's the value?
Exactly. So
the
here,
question.
basically, the main value to Hector, and that's an excellent question, is in these children with cognitive disabilities, such as autism or something, they tend to have a lot of trouble interacting with strangers or adults. In some extreme cases, they may not even want to be in the same room or things like that. So, right, we have this spectrum of possible issues, and this robot is not a human. This robot it's an object, and it may be less intimidating socially to a child who has these issues. And so the idea is, let's use this robot, who isn't a human, to perform these repetitive tasks that the child can observe, perhaps in the same room with the therapist, as in our video example of the robot walking on a treadmill. You still have to have interaction. It's not a completely independent robot. It doesn't have complex sensors to stand up and things, but it can do a repetitive function, visual, and serve as a visual model for that child.
Thank you.
My questions are related to cost. First one, you mentioned you want to design something that would be less than $1,000. Have you achieved, or do you have anything to show that shows you achieved that?
Right. So so far the only estimate that I can provide you, if we go back a couple, is by component-wise, and this is actually missing a few key components that we will use in the final design. So this is just very rough. And to give you an idea, we realize that making a humanoid robot is, it's something that can be a very robust design process. It can be very complex, and we know that we can't necessarily achieve those levels of complexity at the lower price. But we're willing to sacrifice, compared to, say, like the Poppy robot, which is it's capable of doing many more functions. We're willing to sacrifice some of that functionality in picking our servos, maybe less capable servos. For example, with the Poppy, each servo, I'm sorry, I don't know the exact model of the servo, but they range about $400 a servo, whereas the ones we're selecting are in the $40 servo range. So that's one place where we can slash the cost of our robot a lot. The Poppy robot, to give you a frame of reference, costs about $10,000 to make. So we are hoping for under $1,000, but that is a conservative, that is an optimistic estimate, and we will hopefully be in that range regardless.
So your goal is to have this market, right? I mean, the goal, the optimistic goal would be to have one of these robots in every rehabilitation facility.
Well, I think the ultimate use of this robot would be more individual than maybe one robot per physical therapy. It may, or per clinic, it may be that the robot is general enough that it serves its function for many patients, and then it can be used. But really the idea is that each individual caretaker, so for example, parents of an autistic child who are generally very involved in their upbringing, people like that can get involved. And maybe they don't have the technical know-how, but they can hire someone, or the robot is supposed to be individual, basically. Something that not only the therapist can use in the office, but that the child and parents can take home and continue to use at home and improve that continuity of care.
So by you making it less than $1,000, you must have, there must be a benchmark you came out of, right? Professional dealing with an autistic child charges X amount of dollars, and you're trying to make a better solution or an easier solution for a cheaper price. Is that?
So we didn't have necessarily a benchmark given to us by the medical side of the problem. Ours is really, we looked at the average cost of these similar robots, which maybe are more robust, and this came up with, it was almost an arbitrary price point that we tried to hit, and it's pretty close to what we're able to based on the price of different components that we're selecting and such. So the $1,000 price point isn't compared to another existing tool, but rather compared to other existing humanoid robots at the moment.
Okay. So it was not, you weren't trying to make this a product that is more marketable to a specific audience. It was just, you set a goal and you're trying to accomplish it.
Right. In a way, we're not making it necessarily marketable to that specific audience, because it could be that a lot of these families who have these children are also of low socioeconomic status or something, and have trouble affording even something that we reduce the cost to $1,000, right? So we're just doing our best to minimize the cost and overall increase accessibility, because of course a lower costing tool is probably going to be used more, or is a little bit more accessible.
From a maintenance or from a life perspective, you're using lower grade parts, as you mentioned. How is that going to factor into your robot? Is this something that will require a lot of, will it break a lot?
So
since
this
you're
is-
using lower grade parts.
And this
So
is
the main difference between the servos that we are using for Hector, the Poppy, are Poppy use servos that has noise suppressor that make it more like, when they function, they're more attractive per se as a robot. Our servos have the enough torque capacity to have a smooth joint motion, but it doesn't have those fancy features that those servos have. That's when the price difference comes in.
So
Not
the idea
necess-
of having it be an open source is also that the servos can be changed. It doesn't have to be the servos that we're creating. This is like you said, a prototype. In the end, if somebody wants to spend a little bit more money and create order a better prototype, they can get a different kind of servos. This is also like an estimate of what we got with those servos. The main cost here is the servo, because there's 19 of them, but they don't necessarily have to be the same servo. Because this is a servo that's capable of handling the joints of the legs, which have the most weight on them, and then the hip. But if you're going to use a servo for the neck, because it's not required to be that strong, it could be even a more economical servo as well, reducing the price overall.
How many servos can you run at once? Or how many servos do you plan on running at once?
The prototype stage has 20 degrees of freedom. Using Arduino Mega, you can run up to 34 servos at the same time. For our final designs, we are trying to keep the same number of degrees of freedom. It'll be close to 22. We might need to add one for the neck and one for the hip also. Yeah, we will make it like a 22 degrees of freedom. Using the Raspberry Pi and one shell to actually control, you can actually control more servos at the same time.
Have you considered how much current you're going to be drawing in
It's
these?
1.5 amps for every servo in average.
For every servo? So you're gonna
Well,
be
the battery is
pulling-
going to be that range, the range for 1.5 amps.
So each servo is going to pull 1.5 amps, so if you have 20, you're going to be pulling a lot of amperage to be pulling. What wires are you going to be running on this robot?
Oh, well, the capacity of the battery is 1.5, but the servos has they consume less current. It's not 1.5, I'm sorry.
Oh, okay. That makes sense. Have you considered what happens when the robot arm bends and your servo motor wire is in the way?
Well, there is protections for the wires that we are going to implement, and we will make sure that doesn't go through the joint, so it doesn't pinch the wires. That will also be implemented on the final phase.
Another interesting thing is that, so in our picture of Hector over here, really the only thing that's final for a designer, the degrees of freedom and where the joints kind of are. Structurally, we haven't decided that this is necessarily his final form. Shape-wise, we will be able to, maybe adjust the physical structure to account for things like that. Especially child safety, that's something we really need to consider. Just because a child can't necessarily throw it against the wall doesn't mean that they couldn't get a finger stuck somewhere, things like that. So structure-wise, we could still make modifications to account for things like that if the need comes up.
Is it gonna be tethered?
So we're hoping not to. That's the idea. In our first iteration, it's impossible, but in the final design, we're hoping to incorporate that battery, and that's kind of why we need to consider how much amperage we're pulling and those factors.
I strongly encourage you guys to actually design or model the harnessing that's going to go into the robot. You're going to find that it'll be not trivial to account for the movements you're expecting, especially if you're trying to like rotate arms and stuff like that. You're going to have to figure out how you can manage slack in a closed space where someone can't reach, because like you said, if a kid puts his finger inside of it, he can crush his finger, but not only that, he can pull a cable, he can shock himself, and minimum amperage to stop a heart is pretty much minimal compared to how much power you said you could be pulling from your battery.
Right.
So I would seriously consider modeling that, because it's something that's looked over a lot in industry, and it isn't talked about in school. It's super important to mechanical designs.
Thank you.
Thank you. Sorry.
You may want to think about putting almost a stuffed animal around this.
It's an
That
interesting
prevents
thought.
people from touching things.
Give us more space too.
That's actually an interesting thought. One of our focuses, and I don't think we actually touched on it too much, was the idea of making this as 3D printable as possible. So component-wise, the structure, we ideally like it to be completely 3D printed, so the inclusion of like outside material might not be optimal, but it's something that we can consider in addition. You know, as like, here's our default configuration, add these things to increase safety, increase appeal to the child.
Any other questions?
Thank you, dude.